All right, y'all. Today we're going to be talking about infinite limits. And just so y'all know, I'm making this early, so you're not going to have to freak out and do it at the start of class. So, yay, Mr. Arbone getting his crap together. Hey. So, infinite limits are limits where x approaches positive or negative infinity, especially when we have that rational function situation. So, we have f of x over g of x. Okay. And basically, any limit, which is that form, is always going to equal the horizontal asymptote if one exists. So horizontal asymptote rules, if g of x has a higher degree than f of x. So that means if I have a situation like x plus 2 over x squared minus 4, okay, so my g of x, my bottom function, has a higher degree than my f of x. So that means it is bigger on bottom. So what I mean by bigger on bottom is that my degree is bigger on the bottom than the degree on the top, which means my horizontal asymptote is y equals 0. Okay, so bigger on bottom. A nice easy way to remember that is as Bobo. Bigger on bottom, you have 0. Okay. So our next one, if f of x has a higher degree than g of x. So let's just flip that same equation around. So if we had x squared minus 4 over x plus 2. Okay, so now this is bigger on top. Which we say is bottom, B-O-T, bigger on top, than n for none, because we have no horizontal asymptote. We have a slant asymptote instead. Okay, so the one thing about your bigger on top, if you notice, our general rule is that if the limit is as x approaches positive or negative infinity for a horizontal asymptote, if we don't have a horizontal asymptote, it can't equal the horizontal asymptote. So bottom ones are going to be a little bit weird. So just something kind of to note as we're going through these notes today. Okay, now our last one is if f of x and g of x have the same degree. So let's say we have x squared minus 4 on top, and we have 2x squared plus 7 on the bottom. So both of these have the same degrees. So we say exponents are the same. Which we can abbreviate as EATS. Exponents are the same. Now for our horizontal asymptote, we divide the coefficients. So remember, our coefficient is this number here in front. Okay, so whatever number is there in front is our coefficient. So in this case, it is 1 over 2. So our horizontal asymptote in this case would be y equals 1/2. Okay. So our three situations are bigger on bottom, so the degree is bigger on the bottom. The horizontal asymptote is y equals 0. If it's bigger on top, then we don't have a horizontal asymptote. We have a slant asymptote. And then if they are the same, if our exponents are the same, then our horizontal asymptote is the coefficients divided. So to help you remember, kind of short little trick, little mnemonic phrase, Bobo Botten eats DC. Bigger on bottom, y equals 0. Bigger on top, none. Exponents are the same. Divide the coefficients. Okay, so let's look at some examples. So the limit as x approaches infinity of x minus 1 over x squared plus 3. So I look at my coefficients. I have 1 and I have 2. So it is bigger on bottom. So horizontal asymptote is y equals 0. So my limit is 0. Notice how I didn't even care whether it was positive or negative infinity. Because it was bigger on the bottom, I just automatically go to it being 0. Okay? So I'll get another one. So we have 5x minus 2x cubed plus x squared over 3x minus 2x plus 1. So one thing to notice, it's not always the first term. It is what we call the leading term. The leading term is always the term with the highest degree for each of our equations. So this one's a little tricky, but I find an x cubed and x cubed. So this is exponents are the same. Divide our coefficients. So our horizontal asymptote is y is equal to -2 over +3, which is -2/3. So that is our limit. Nice and easy like so. Okay. Now up here in the top right, we have -x squared plus 3 over x minus 4. So it is squared over 1. So it is bigger on top. Okay, so since it is bigger on top, we do not have a horizontal asymptote. We have a slant asymptote. So I'm going to teach y'all just a little quick trick. Yes, it's kind of a cheat code. I can show you the full algebraic method if you want the full algebraic method, but you have to plug in numbers. It's a little bit too much work. So I like my cheat code. And really, as long as you know there's a slant asymptote, that's all that's really important. Okay, so I'm going to make a little graph, and it's going to be the roughest sketch of a graph ever. Okay. So just as a reminder, this is our x-axis and our y-axis, and this is positive and negative infinity in all of our directions. So just remember, if I went up forever, or if I went down forever, that would be positive or negative. If I went to the left forever, that's negative infinity. If I went to the right forever, that's positive infinity. Okay, so looking at this, the first thing I'm going to look is I'm going to kind of guesstimate at what my slant asymptote would be. So you find a slant asymptote by doing long division. And when you do that long division, what you find is that the slope of that slant asymptote follows along with your leading coefficients. So I have -1 over 1, which is a negative slope. So I'm going to just real roughly act like that's my slant asymptote. Notice I don't have any numbers anywhere. The only thing that's really important to me is that it's a negative slope because I have a negative set of leading coefficients. Okay. The next thing I'm going to do is I'm going to look at which infinity I'm going to. So my x is going towards negative infinity. So I'm going to start here with my function, and I'm going to follow along from the opposite side of where I'm trying to go. So I'm going to go towards negative infinity, and then when I run into my asymptote, I'm going to follow along my asymptote. Okay? So if my function kept going up in that direction, what is it going to go towards? It's going to go towards positive infinity. So my answer here for my limit is positive infinity. Now, you might be right now like, Mr. Arbone, that just looked like a bunch of mumbo jumbo. And you might be a little correct. So real quick, hopefully you can still see my screen. I don't know, maybe you can't. I don't think you can see it, so we're not going to risk it for today. But if you ask, I will show you a graph on Zoom in class on Wednesday or Thursday, proving to you that that is solid math. Okay, but when we are looking at a bottom, there's two things you look at. You look at the leading coefficients to know if you need to draw a negative slant or a positive slant, and then you look at which infinity you're going towards to know if you're going to go from right to left or from left to right. Okay, and then it's just either going to be up towards positive infinity or down towards negative infinity. Okay, last but not least, we have the square root of 4x squared plus 1 over x minus 2. Okay, so this one is super weird because we have that square root on top. But what I want you to do is we're going to kind of cheat a bit once again. Okay, one thing you're going to notice about calculus is sometimes we can ignore things, and it's really like the greatest thing ever. So I'm just going to look at that square root of 4x squared. So if I just look at that, that's technically the same thing as positive or negative 2x. Okay, I don't know which one it is because it's a square root, so I get both a positive root and a negative root. And then I'm looking at it over my other leading term, which is x. So that would be EATS-DC. Exponents are the same because they both have an exponent of 1. So if exponents are the same, then my horizontal asymptote is y is equal to positive or negative 2, because I have to consider both of those points. So as I look at this, you're like, well, Mr. Arbone, if it's approaching two different numbers, then how do I know which one the limit is equal to? Well, we want to know which direction the negative infinity one is going to be, because we're heading towards negative infinity. So if you had a calculator, this would be a really easy one to figure out, because I would either I would just graph it and look at it, and that would be really easy, or I'd plug a number in and I'd be able to get something out. But unfortunately, I don't have a calculator, so we're going to have to think just a little bit intuitively. Okay, so on one like this, I want to know what's happening as I go towards negative infinity. So I don't need to pick, a super huge number, but I do want to pick a number in the negative direction. So let's say negative 10. So I'm going to plug in negative 10 real quick. So the square root of 4 times negative 10 squared plus 1 divided by negative 10 minus 2. Okay, so when I take this, that negative 10 squared, that's going to be 100. So really we get the square root of 401 divided by negative 12. Okay, so what's going to happen is that as I head towards negative infinity, no matter what, because whatever x value I plug in there in the top is going to give me a positive number. So I'm always going to have a positive number under the square root, which is good. I want to have a positive number under the square root. But I'm always going to be dividing that positive number by a negative 12. And because I'm going in the negative direction, that square root of 401, I'm really only going to be considering the positive solutions from it. So if I'm always taking a positive number and dividing it by a negative 12, then that's always going to equal a negative number. So which of the two horizontal asymptotes am I going to be approaching? Well, I'm going to be approaching negative 2. So the limit as x approaches negative infinity would be negative 2. All right, let's look at some more. So we have the limit as x approaches infinity of x to the 100th power over 2 to the x. Okay, so before we get going too much on these, all 4 of these situations on the second page of notes are kind of your extraneous. They're a little more difficult. So if you're like, I'm not feeling so hot about these, don't worry about it. Okay, they're not going to pop up as often. So don't feel like you're like, I have no idea what's going on if you don't know these 4. Okay, so let's look at our first one. We have the limit as x approaches infinity of x to the 100th power over 2 to the x. So unfortunately, we can't really compare x and 100 because x is a variable. That doesn't make any sense. So let's go back up to the top right here. As a general rule, factorials are greater than exponentials. Exponential functions are greater than polynomial functions. Polynomial functions are greater than a linear function. And linear functions are greater than logs. What that means is it means if I was to plug numbers into these types of functions, the value that I would get out would go in kind of this order of greatest to least. So logs are our least, factorials would be our greatest. So let's look at the 2 functions that we have here. X to the 100, that's a polynomial. Yes, it has an exponent, but all of our polynomials have an exponent. To the x is an exponential. Remember, what makes something exponential is that it has the variable in the exponent. Okay, so looking at our list, exponential functions are greater than polynomial functions. So what that means is that as I start to plug x values in, eventually over time, as I go towards positive infinity or towards negative infinity, my exponential function is eventually going to be greater in value than my polynomial function, no matter what. No matter what polynomial function I have on top, an exponential function is always eventually going to be greater, which think about that. Right now, so let's say I plugged in 2. 2 to the 100 would definitely be bigger than 2 squared. okay? But then 100 to the 100 over 2 to the 100, okay? Well, now 2 to the 100 is not that far off. And if I keep going, so let's say 1,000 to the 100 over 2 to the 1,000. So now, yeah, I'm multiplying 1,000 by 1,000 100 times, but I'm multiplying 2 by 2 1,000 times. So that one's actually going to be bigger. And as I get bigger and bigger and bigger, so what's going to happen? Kind of think about this as like infinity over infinity plus. This is always going to be a bigger infinity, okay, eventually, because it's an exponential dividing a polynomial. Exponential functions will always eventually be bigger than a polynomial function. So if the number on the bottom is always going to be bigger, and I divide a number on top by an infinitely bigger number, so think about this. If I divide 1 by 2, that's 1/2. If I divide 1 by 4, that's 1/4. 1 by 8, 1/8. 1 by 100. My number is getting smaller and smaller as the number on the bottom gets bigger. So if my number gets infinitely bigger, if I divide something by infinity, it's going to be a really, really, really small number. So we can essentially say it's equal to 0. So anytime the bigger function is on the bottom, then our limit's going to be equal to 0, because that bigger function, that bigger infinity, is going to end up basically getting so big that the function essentially equals 0. Okay, now let's talk about another one. We have the limit as x approaches negative infinity of x to the 100 over 2 to the x. Same function, but now we're going the other way. Now what makes this one a little bit different is that if I plug in infinity to the 100 over 2 to the negative infinity, well, now I have a negative exponent. And before I evaluate anything, I always have to make exponents positive. So we know our exponent rules. A negative exponent means move that exponent up to the top. So we get infinity to the 100 times 2 to the infinity. So now I'm no longer looking at a fraction. Now I'm just looking at a really big number times a really big number, which is just going to be equal to a really big number. So that's actually kind of nice, because I don't even have to think about the fraction. I don't have to think about which function is bigger. I just know that it's a big number times a big number. They're both positive, so it's positive infinity. Okay, the limit as x approaches infinity of x over natural log of x. So this time we have a log function and we have a linear function. Linear because it's just x to the first power. So looking back up at our list, a linear function is greater than a log function. So as I kept going, so if I wanted to go to, like, say 100 over the natural log of 100, well, 100 is a pretty big number. The natural log of 100 is always going to be a decimal. Okay, remember, anytime we plug a number into a log, a positive number at least, we always get a decimal out. So I'm just going to be dividing bigger and bigger numbers by a decimal. Dividing something by a decimal makes it even bigger. So eventually, this will just equal infinity, because the big number is on top of the function. So an infinitely bigger number divided by a smaller number is just going to be an even bigger, infinitely big number. So positive infinity. All right, now last but not least is sine of x. And sine of x kind of operates outside of all these different norms. If you noticed up here, one of the functions we didn't include trigonometric functions. Because what does sine do? Well, for the entirety of a sine function, it goes up and down and up and down and up and down and up, like so, forever. Because sine functions, and really all trig functions, do what we call oscillate. They repeat over and over and over and over and over again. Okay, so if it's going up and down and up and down and up and down, is it ever really approaching a singular y value? Well, no, because it's going to go up to positive 1 and then back down the negative 1, and then up to positive 1 and then back down the negative 1. So since it never really equals anything, we would actually say that this limit doesn't exist. Because I can't say it's both 1 and negative 1. That doesn't make any sense. So we just say that it's D and E. Okay. So limits equaling infinity. Remember, we have the ones at vertical asymptotes that we did last class with our algebraic limits. And then we also have our ones at horizontal asymptotes that we did today, our Bobel-Bond eats DC. And then down here you have kind of those extraneous, those weird situations where you have to think about the function on the top and the function on the bottom and which one's bigger. So go ahead and finish out the rest of these, complete these practice problems down at the bottom, and then we'll be working through station 10 and 11 today in class.